Hey everybody. Today we're approximating alternating series using partial sums. So first of all, let's remember what an alternating series is. It's one where adjacent terms always have opposite signs. So plus, minus, and so on. A lot of times we write them in the form sum -1 to the n, a sub n, where the general term a sub n is always positive. Your most basic example is the alternating harmonic series, 1 minus a half plus a third minus a quarter, and so on. There's a very simple test for convergence in the case of alternating series. If you have an alternating series and the general term an is decreasing and going to 0, then the series converges. So in general, it's difficult, if not impossible, to actually find the sum of a series, even an alternating one. And so the thing you want to do is to approximate the overall sum just using a partial sum, Sn. That's only really useful, however, if you can say something about how wrong your approximation is going to be. In other words, how good or bad that approximation is. In the case of an alternating series, there's a very simple formula for that. En, the error in the partial sum for doing just the first n terms of the series, is defined to be, of course, the absolute value of the difference between that partial sum and the overall sum. And in this case, it's going to be bounded no worse than the next term in the series. So if you take the first n terms, the error is going to be no worse than the n plus first term. Here's an example. Using the first 9 terms of the alternating harmonic series, we get 1 minus a half plus a third all the way up to plus 1/9, which is about equal to 0.7456. So the error on that can be no worse than the next term in the series in absolute value, which is a tenth. So 0.7456 is guaranteed to be within 0.1 of the full sum of the series. Again, more generally, the error when you use the first n terms to get the nth partial sum is going to be no worse than the next term, 1 over n plus 1. For instance, S sub 99 is going to be within 0.01, and S sub 999 is going to be within 0.001, and so on. Example 2. Estimate the following series so that the error is no more than 0.0001. And I'm looking at the sum from n equals 1 to infinity, -1 to the n plus 1 over n to the fifth. This is an alternating series. Notice that it's decreasing and the general term goes to 0, so this is actually going to converge. Now we can actually try and estimate it. Now, we know that we want the error to be less than 0.0001. So if we use n terms, the error is going to be less in absolute value than the n plus first term. So 1 over n plus 1 to the fifth has to be less than 0.0001. Our goal now is to solve this for n. So we cross multiply, take the fifth root and subtract 1, and then get a decimal approximation, about 5.3. Now we always want to round that up. We always want to take more terms, not less, in order to reduce error, not increase it. So 6 terms is going to be sufficient here. Here's what we get when we use the first 6 terms of the series: 1 minus 1 over 2 to the fifth plus 1 over 3 to the fifth, and so on. Overall, 0.9722. It's guaranteed that this approximation will be within 0.0001 of the sum of that full series.